Good morning, everybody. Welcome to Mr. Newbert's amazing video lessons, first in a series of lessons as I'm becoming more technologically advanced here. Hopefully everybody is healthy and staying well. First things first, I want to get through this lesson with you on acceleration. We're doing acceleration. If you have not read the acceleration section, chapter one, section 3, or done the directed reading guide, then pause, hit the pause button. That's right here. Hit the pause button and read it, do the directed reading, and then start playing the video from here. If you have work that you've not completed from the first couple of sections, hit the pause button right there, and please get that work in to me, submit it. We understand there's some circumstances where you cannot submit things, or so get those in, please, and then play the video. All right, so let's start right from the top. Turn to page 22 in your book. You should have your blue book. Open to page 22. You're also going to need your access to some of the worksheets. I'm going to go through all the practice sheets, go through the homeworks, go through the review, go through the roller coaster video you're going to be doing and what you're going to be watching, and then finally the guided study. So you can pause it anytime you want to and replay. This is all new to me, so I'm trying to do this in one take. There's probably going to be some flubs, so get used to it. It's going to be a low-tech adventure, trust me. All right, so acceleration. We know acceleration is speeding up, and you get on the highway. You're on the roller coaster. We're going to talk about coasters a lot today. You're on the Top Thrill Dragster, and it has a rapid acceleration. Okay, speeding up. You hit the accelerator in your car. You speed up. It can also be slowing down as well, as you read about. So speeding up, slowing down, acceleration, we call that positive acceleration. Deceleration, we call it negative acceleration as well. But there's also a third thing. So it can be speeding up, acceleration can be speeding up, slowing down, or, anybody? Changing direction as well. The reason for that is, and you've already read the formula, acceleration is a change in velocity over time. Change in velocity divided by time. If you recall from the first section, velocity is speed plus, what is it? Direction, right. Speed plus direction. So if you're changing your speed, you're accelerating, whether you're speeding up or slowing down. If you're changing direction, it's one of those by definition, one of those science things by definition. If you're changing direction, you are accelerating. Okay, it's a form of acceleration by changing direction. Since if you're going 10 meters per second, that's speed. If you're going 10 meters per second north, that's velocity. If you now change from 10 meters north to 10 meters per second south, you've changed direction. You're going at the same speed, but that's called, we consider that acceleration. You're riding your bicycle down a hill. You're accelerating. You're picking up speed. That's acceleration. You hit a hill. You start to slow down. That's deceleration. You're riding your bike around the block at a constant speed, constant velocity, we're going to say. You're changing direction, but it's at a constant speed. You're just changing, you're also accelerating. Okay, it's one of those things that we're not going to use that in any of the formulas, any of the problems today. Where the objects you're going to be looking at are speeding up or slowing down. Okay, but by definition, the changing direction is accelerating. All right, flip it a page 24. If you look at the top of the page, you have a nice little airplane. Notice the clock at the top. Notice the airplane. Notice the speed. What's happening to the speed as the plane goes down the runway? It is increasing. And by how much is it increasing? Every second. Take a look at that. Right, it's increasing by 8 meters per second every second. Okay, 8 meters per second every second. That's an example of acceleration. That's a constant acceleration. It's speeding up by the same amount every second, 8 meters per second every second, we would express that acceleration, we'll get to this a little bit later, as 8 meters per second per second. Take a look at the yellow box. There's your formula. Acceleration equals final speed, or we're going to call it final V, V for speed, V for velocity, minus the starting speed. They call it initial, I call it starting speed, to make it easier to remember, divided by the time. It has to be final minus starting, divided by time. If you take starting minus final, you're going to get a negative number in some cases, and that's going to tell you that it's slowing down. Remember negative acceleration? That would tell you it's slowing down. Okay, look at this problem with the airplane at the bottom of page 24. Acceleration is 40 meters per second. That's the final velocity of that plane. It started out at 0 meters per second, divided by 5 seconds, the time it took to get on the runway. So 40 minus 0 gives you 40 divided by 5, which gives you 8 meters per second squared. They call it meters per second squared. I prefer to call it meters per second per second. No, I didn't stutter. That's how you express it. Let me explain this, why I do that. Meters per second can get confusing to people. All of a sudden they see the exponent, they start squaring the number and get all kinds of crazy answers. So meters per second makes more sense to me. Okay, you're in a car getting on the highway. You're doing 0 miles per hour. The light turns green. You hit the accelerator and you're speeding up. After 1 second, you guys can see this is the high-tech illustration here. V for velocity is in miles per hour. We're going to do miles per hour here because we're in America. We use miles per hour, but in science we're using metric. So for this example, we're going to start with miles per hour. Time is going to be in seconds. After 0 seconds, you're at the red light. Okay, the speed is 0. After 1 second, your speed is increased to 10 miles per hour. After 2 seconds, it's up to 20. 3 seconds is up to 30. 4 seconds is up to 40. What's your acceleration? How much you're speeding up? How much you're accelerating every second? Correct. 10 miles per hour every second. So you'd express that as the acceleration is 10 right here, 10 miles per hour per second. So you went up by 10 miles per hour every second, 10 miles per hour per second. Okay, now I'm just going to change the labels on this. And there goes my marker, just hit the floor. Again, we're not stopping for anything. One take. Found it. So we're changing the labels from miles per hour to meters per second. Okay? And time is going to be still in seconds. Okay, so now we just changed the metric, not a direct conversion to miles per hour by any means, but most of the problems you're going to use is going to have meters per second as the speed. So meters per second in seconds. So after 1 second, the object is going 10 meters per second. After 2 seconds, it's going 20. After 3 seconds, 30. 4 seconds, it's going 40 meters per second. So every second it's increasing by 10 meters per second. Okay, instead of miles per hour per second, it's accelerating by 10 meters per second. This isn't Khan Academy. Here we go. 10 meters per second. Okay, right here. Okay, so I like that. I like using that label for units instead of meters per second squared. It's a little more confusing. I think meters per second tells you more how much it's speeding up by this much speed. It's going up by 40 meters or 10 meters per second. Move my finger per second. So it's going up by 10 meters per second every second. Okay, that airplane Down the runways increasing by 8 meters per second every second. Okay, take a look at calculating acceleration. You got a roller coaster. We're going to talk about roller coasters. Let me know what your favorite roller coaster is that you've ever been on. And we'll do a little survey. That'd be kind of fun. Just send me a little comment about your favorite roller coaster. As a roller coaster starts down a slope, its speed is 4 meters per second. But 3 seconds later, at the bottom, its speed is 22 meters per second. What is its acceleration? If you look in the book, they do the problem for you. The starting speed or initial speed is 4 meters per second. That's in blue. Final speed is 22 meters per second. Time is 3. They plug it into the problem, into the formula. A equals final V divided by starting V over time. 22 minus 4, which is 18, divided by the time of 3 gives you 6 meters per second. So that coaster is accelerating at 6 meters per second, which is a speed, 6 meters per second, every 1 second. Okay. There are 2 more problems here. Math practice, you can pause this. Please pause it and do 1 and 2. A falling raindrop accelerates from 10 meters per second to 30 meters per second in 2 seconds. What's the raindrop's average acceleration? And then a certain car can accelerate from 27 meters per second, from rest, I'm sorry. So when it says from rest, it's from 0, starting point of 0 to 27 in 9 seconds. Find the car's average acceleration. Hit the pause button and solve that on some scratch paper. Are we back? Here we go. Hopefully you got those solved. So on the first one, it's going to be 30 meters per second instead, raindrop. Final velocity is 30, so it's 30 minus 10 divided by 2, which gives you 10 meters per second is the acceleration of that raindrop, which also happens to be the acceleration due to gravity, rounded up a little bit, how fast things accelerate towards the earth when dropped due to gravity, gravitational pull. We'll get to that in the next chapter. The second problem, certain car is accelerating, so it's 27 minus 0, because the starting speed was 0. 27 minus 0 divided by 9 seconds gives you 27 over 9, which is 27 divided by 9, which is 3 meters per second. Okay? All right, next, some practice problems. You can access the acceleration practice sheet, this one here. If you can access that one somehow, maybe on a split screen, you know how to do all that stuff. Okay, or you can pause this and look at it as we go. Okay, but I want to go through this thing. I want to start you on the problems here. Top of the page, acceleration means a change in speed or direction over a period of time. It can be defined as a change in velocity per unit of time. There's a formula for you. A equals FV minus SV, final minus starting, divided by time. And there's some units to use. Velocity is in meters per second, or can be kilometers per hour. Can be minutes per second, can be minutes per hour. Or meters per hour, rather. Time is in seconds and hours. And acceleration, the only ones we're going to use here is meters per second, and kilometers per hour per second. The roller coaster video that you're going to be doing later today, or later this week whenever you get to the roller coaster video, is going to be in miles per hour per second, because all the coaster speeds are in miles per hour. Okay, first problem. These are all examples. You can do these on your own. If you want to fast forward, I'm going to be going through these. If you've got a good handle on it, that's fine. If you want to go through this with me, I'm going to go through it. Number 1, they give you on all these, they give you the starting velocity is on the left, final velocity is on the right, and there's your time. So it's simply final minus starting over time. So 24 over 0 divided by 3, which gives you 8 meters per second. So your setup should look like this. If you can see this at the top of the page, you should have your formula and then plug in the numbers, and then A equals 8 meters per second per second. So when you're doing your homework problems, you need to write your formula for every single problem, plug in the numbers directly underneath, not left to right, but top down, just like in math class, and then divide, gives you 8 meters per second per second. Make sure it's final minus starting. It has to be final minus starting. Number 2, final is 35, starting is 0, so it's simply 35 minus 0 over 5, which gives you, magically, 7 meters per second per second. The third one gives you, this one's a little different, okay? Starting is 20, final is 60. Things don't have to start at 0, and that's in 10 seconds. So you should have 60 minus 20 divided by 10, which gives you 40. Just do the subtraction, 40 and 60 minus 20 gives you 40 divided by 10, which gives you 4 meters per second per second. Okay, so far so good, clear as mud. Fourth one, it's a little tricky. Final minus starting. Your starting is 52 meters per second. Your final is 27 meters per second. So what's the vehicle doing? It starts at 52 and ends up at 27. It's slowing down. It's decelerating. It is negative acceleration. So make sure you put the numbers in the right spot. Run. Not the last one. That one there. So it's 27 minus 52 over 5. Okay. You have to subtract. It has to be 27 minus 52, which gives you negative 25 over 5, which gives you negative 5 meters per second per second. These numbers can be have a negative, which tells you it's negative acceleration. It's slowing down. Okay, negative 5 meters per second per second. So it's a plane landing, or it's a roller coaster coming to a stop. Let's do coasters. Roller coaster, the blue streak's coming to a stop. It enters the station after your ride. It's slowing down at a rate of 5 meters per second per second. It's decelerating. It's negative acceleration. The last one, different units on this one. Okay. This one is the starting is final. I'm sorry. Starting 0, final is 120 kilometers per hour on this one. So it's a slightly different unit, okay? In 6 seconds, I think the time is, okay? So it's 120 minus 0 over 6, okay? Which magically gives you 20, hold on a second, 20 kilometers per hour per second is how to express that one. 20 kilometers per hour per second. Okay? And we got cats wandering all over the studio here. Yep, now he's going to go on the treadmill. Nope. And it's a stampede. All right, here we go. Acceleration worksheet. Pull up the acceleration worksheet. That's this one here. I'm just going to give you do the first one with you and then turn you loose on that. We're about 20 minutes in, probably about another 10 minutes. We'll be done. Okay, acceleration worksheet. Again, there's your formulas. Final velocity minus starting velocity. A equals FV minus SV divided by T. Every problem needs to have that formula. You plug the numbers underneath it, solve it, label it, just like the instructions say. There's your units, meters per second, kilometers per hour. Time is seconds or hours. Acceleration, meters per second, or kilometers per hour per second. Okay, take a look at number 1. I'm just going to do number 1, and then I'll point a few more things out. car is increasing its velocity from 0 to 14 meters per second in 2 seconds. By now you should have a handle on its final minus starting. 14 minus 0 over 2 gives you 14 divided by 2, 7 meters per second per second. So the car is speeding up by 7 meters per second every second. Okay. The rest of the problems are similar. Number 3, be careful because it decreases. That's why I bolded it, so you point that out. Be careful. Number 4, the train's already moving. Okay, train's already moving, and it's speeding up over 12 seconds. Okay, the rest of those are pretty similar to what we've been doing, except they're in a story problem situation. Okay, next, pull up. Actually, okay, let's stop there with the acceleration. Let's flip back to your book for a second. I'll point out a couple things. Flip the page to 26, 27. Got a couple of graphs, and I know we've done graphing already in the last week. I may revisit that and teach that with a video now that I'm the expert video YouTuber. I may reteach that. I'm probably going to reteach that just because some people are confused by that, having to do it without instruction, direct instruction. So I'm going to probably revisit that for people who want to tune in and watch that. It's going to be a great show. Page 26, you got a speed and time graph. Okay, speed and time graph. If you look at it closely, the purple line is going up how many meters per second every second? 2. 2 meters per second every second. After 1 second, it's at 2. After 2 seconds, it's at 4. After 3 seconds, it's at 6. Okay, meters per second. So it has a constant acceleration of how much is it going up by every second? Going up by 2 meters per second every second. And that's what that straight line shows. So a linear line, it just shows a constant acceleration. Not constant speed, because the speed is going up. It shows constant acceleration of 2 meters per second. Just like that airplane going down the runway. Okay. Acceleration on a distance and time graph, which is on page 27. Now we're talking about distance on the x-axis and time on the y-axis. Okay, so now we've got a change in speed. Change in speed. What's change in distance? What's on page 26? The speed was increasing at a constant rate. On page 27, the distance is increasing. Okay. And it's increasing dramatically, like that little airplane going down the runway. The distance increased over time. So after 2 seconds, it's traveled about 5 meters. After 4 seconds, it's up to 15 meters. Okay? After another second goes by, it jumps up to 25 meters. Okay? So the distance is increasing rapidly over time, which is what acceleration is. Increasing distance over time. If you're traveling the same distance over time, then you're not accelerating. It's the same speed. All right. Next thing. Flip over to pull up your roller coaster acceleration video activity. Your roller coaster. Okay? Give me a second to pull that up. Pause it. Pause button. Okay, you are back. Watch the roller coaster video. There's the link for the roller coaster video. Take note of the following coasters: top speed and time. Time is given. If not, I'm giving you the time on the handout here. If it's not in the video, sometimes the video will say something increased to some speed over just under 4 seconds. I gave you the exact time on those. Okay, so use the times that are on the sheet. If not, you're going to have to pull it out of the video. So watch the videos. There's top 10 fastest coasters in the world. Back up top. Solve each coaster's rate of acceleration using starting velocity of 0. They're always starting from 0, whether it's on the top thrill dragster, where it starts at 0 and you rapidly accelerate. do 120 miles an hour in 4 seconds. Or if it's at the top of, let's say, the Millennium Force, you're at the top of the hill going 0 vertically. You're still moving forward horizontally, but vertically you're going 0, and then you accelerate to the bottom to 93 miles an hour in so much time. Okay, so your starting velocity is always going to be 0. These are easy to calculate. You're always going to be using 0 as the starting velocity, and then the maximum speed is your final velocity in whatever time either I give you or the video gives you. All right, and you can hear that bell. Yes, Nemo's telling me it's time to go. So use the coaster's highest speed as the final velocity in miles per hour. All units for acceleration will be in miles per hour per second. So make sure you label that. Again, write the formula for each one. Plug in the numbers underneath. Work top down, just like in math. Solve for acceleration and label. Again, miles per hour per second. You've got the Ring Racer, Superman, Escape from Krypton, Top Thrill Dragster, Dodonpa, Kingda Ka, and Formula Rossa, which is the fastest coaster in the world. There's a place for you to do your work, and then answer which coaster had the greatest rate of acceleration. Underneath that, write what your favorite, your personal favorite coaster is, wherever you've been, Cedar Point or elsewhere. I'm kind of curious about that. Okay, have fun with that one. It's a great ride. It's from your perspective going down these coasters. Hopefully you enjoy it. Hopefully Cedar Point will be open this summer. Next, you've got review and reinforce. Okay, we're not going to go through that, but that's pretty straightforward. There's 6 true and false. If it's false, there's a word that's underlined. You have to change that word to make it a true statement. And a couple of graphs at the bottom. And then there's 2 problems at the bottom where you have fill in the blank. So that's pretty straightforward. All right, last but not least, and then you're free to go. Not sure what that was. All right, take out your guided reading and study, which you have completed. Oh, that was a cat jumping on the TV. That's nice. Meanwhile, take out your guided reading. Pull that up on your screen. I want to go through the answers with you. A little bit of review. Okay, what is acceleration? The rate at which velocity changes. Acceleration involves a change in either blank or blank, speed and direction. Okay, so that's why you can speed up, you can slow down, or if you're changing direction, that Cedar Point, you're on the merry-go-round. Okay, those exciting rides. You're going. Are you accelerating on a merry-go-round? If it's going at constant speed, yes, because you're changing direction. Every time you're going around a circle, you're changing direction. So that's an example of acceleration. Anytime speed of an object increases, the object undergoes acceleration. Okay. And also anytime direction changes. Following sentence, true or false? Acceleration refers to increasing speed, decreasing speed, changing direction. Yes, got a handle on that now. Deceleration is another word for negative acceleration. Okay? Deceleration, so we have negative acceleration. Remember, if something's slowing down, it's going to have a negative sign in front of it. It's going to be negative whatever. Is the following sentence true or false? An object can be accelerating even if its speed is constant. True. Like that merry-go-round, or the bicycle going around the block at a constant speed. 7. Circle the letters of each sentence that describes an example of acceleration. A says a car follows a gentle curve in the road. It's accelerating, going around a curve. A batter swings a bat to hit a ball. Yeah, his bat is moving around in a circle, so he's accelerating the bat. He's actually speeding up the bat speed, going from 0 to some speed. This goes 2 ways. And C says a car parked on a hill doesn't move it all day. No, that's not acceleration. Unless you want to include the Earth is rotating on its axis, but we're not going that far. A runner slows down after finishing a race. Yeah, deceleration, negative acceleration. 8, the moon revolves around Earth at a fairly constant speed. Is the moon accelerating? Is it? Yes, it's going around us. It's orbiting us, right? It's revolving around the Earth in 29.5 days at a pretty constant speed, okay? At a constant speed. You got a table down there, acceleration. In everyday language, speeding up is the first one. Increasing speed, we call that acceleration. In more scientific languages, acceleration or positive acceleration. Everyday language, slowing down. In scientific language, decreasing speed or deceleration or negative acceleration. Turning is everyday language. Scientific language, changing direction. Okay. 10. What must you calculate to determine the acceleration of an object? Change in speed over some period of time. Speeding up, slowing down over some period of time. What's the formula? Final minus starting. It has to be final speed or final velocity minus starting divided by time. Okay. True or false? To calculate the acceleration of an automobile, you must first subtract the final from the initial. No, it's final minus starting, so that's false. Has to be final minus starting. 13, we're almost done here, folks. Been a valuable 30 minutes of your life. If an object is moving, which of these are true? If an object is moving without changing direction, then its acceleration is the change in its speed during 1 unit of time. That's true. Because it's going in a straight line and changing its speed. If an object's speed changes by the same amount during each unit of time, then the acceleration of the object at any time is the same. That's true. Okay. So it's going up at a constant acceleration of 8 meters per second per second. And then D is also true. If an object acceleration varies, then you can describe only average acceleration. True. You can't pinpoint exactly what the acceleration is if it's rapidly changing its acceleration. 14. The graph above shows the motion of an object that is accelerating. What happens to the speed of the object over time? It increases over time. The line on the graph is slanted and straight. It's linear. So what does the line show about acceleration of the object? Constant acceleration. Okay, it's going up by a certain amount of meters per second every second. Okay, it's constant with that straight line. That's it. That's all I have for today. I hope this was helpful. If you get it, that's great. If you need the help, that's great. So I'm here for. You can email me if you have any further questions. Looking at setting up some other communications with you guys. Google Hangout, I guess it's called. So I'm going to be setting up that for specific questions. Please email me or send me comments on homeworks if you have any questions or anything that you need help with. If something doesn't upload or download or whatever load, I've had those already. Some students have helped me solve some issues with some videos not playing and things not being loaded. Please use the Google Doc for your answers. Type them on that. Please don't shoot a picture of it and send it. With so many things to grade, hundreds and hundreds of things to grade each week, it helps if it's all consistent, that we use the same document so I can go through it and look for any advice I need to give you. Comments. Look for comments on some of your papers. If you missed a lot, I'll send comments. I'll make corrections on some. I'll have you redo some if you missed too many. Please get them in. And I understand everybody's situation is different. Please get them in as soon as you can so I can get through the grading. Submit them by the end of the week. You've got till Friday to get all these done. Some we just did together, started on some of them today already. So that's about it. Hope you enjoyed it. Hope you guys have a good week. Keep in contact. Hope everybody's safe and well. Stay healthy. Stay at home. And spend some time with your family. So yeah, I miss you guys.